All right, so here we have an acid-base reaction. We've got a weak acid, acetic acid to be exact, added to water. When we do this, remember that we can label something as an acid and something as a base. In this particular case, we're going to label that acetic acid as the acid because it has the proton that it's going to donate to create our hydronium ion. So that makes water our base in this particular reaction. And then the conjugate base of the acetic acid is the other product. Okay? Now, one of the things I want to remind you of is from chapter 15, the Le Chatelier's equilibrium principle. That principle states if you shift or if you agitate either side of that reaction by adding more of something or removing something, that equilibrium has to shift to adjust. Okay? So in this particular case, if we add more acetate ion, which is this guy, Le Chatelier's principle says that if we add more of something on this side, that everything will shift this way. Correct? Remember that. Okay, if I add more acetic acid, aka stuff on this side, Le Chatelier's principle states that we are going to shift everything to the right. Okay, so that being said, the common ion effect is going to basically just be a version of Le Chatelier's principle. It states that when it comes to a strong electrolyte or a weak electrolyte, when we add more of something that a solution has in common with an equilibrium state, that state has to shift as a response. So in other words, if we add more of the acetate ion to the solution, then the equilibrium must shift. Okay, so it's just a restatement of the Le Chatelier's principle related to what we call common ions. The ion in common is really just something that already exists in the equilibrium equation. Yes, ma'am? Say again?
What did you say would shift?
The equilibrium must shift when you add something to either side of an equilibrium situation. Now, when we say common ion, we can mean a number of things. In particular, we can mean that we add more acid. We can mean that we add more of that conjugate base. Now, when we add those things, they do not necessarily have to be acid or base forms. They could be salts. Okay? So in this particular case, we've got a fluoride ion. And it says to calculate the fluoride ion concentration and the pH of a solution that gives us 0.2 molar HF and 0.1 molar HCl. So the actual equation is that of HF interacting with water. So what is our acid-base equation then? Remember that we're going to take our acid, we're going to add water, we're going to form, because this is our acid, technically the hydronium ion, right? Plus the conjugate base of the original HF. We are told, in this particular case, what we start with. We're given a Ka. Anytime you see a Ka, a Kb, a K anything, the first thing you should be hoping to be able to write is an expression, like the one you see at the bottom here. We were given what that Ka is equal to. Remember, it's always products over reactants. From here, we have to recognize, yeah, one of these things makes total sense. The initial concentration of HF is one of the things we were blatantly given, correct? Okay, the other thing we were given is HCl. There's no HCl here, is there? But HCl is an acid, right? What would it give up? It would give up an H+, wouldn't it? In doing that, what it does is act like the H3O+ on the right side of our reaction. So it gives us an initial 0.1 molar for the H3O+ in our ice table. When acids are the common ion, usually they're pretty obvious, right? HCl is an acid. HCl is going to give up an H+, which is going to increase our hydronium ion concentration. Because we were told that information, this is how we're going to work with our ice table. All right, our goal was what? pH and F- concentration, wasn't it? So what is the fluoride ion concentration? So F-, and what is the pH, which means we would need the equilibrium concentration of this guy, right? Do you agree? You remember that from last chapter in our acid-base equilibrium? Okay, so what do we do next? Let's do X's. We're going to subtract from the left. Why are we subtracting over here? Well, if I put, so let's do the thought exercise. If I put negative x over here, does that make any sense? No, because of this 0, okay? Please do remember that the x's, if they had a thing in front, like if this were a 2x, it's because this is balanced to have a 2. Don't forget that from chapter 15. We haven't seen that yet, but it's something we may come across later in this chapter, okay? All right, what are we going to do next? We're going to drop it down. In this chapter, we're going to introduce the concept of ignoring changes in x. There are rules for doing so. Normally, I'd make you go through and solve a pretty intense quadratic equation, right? There are certain situations where we can assume that the change in x is so small that it won't affect the overall number. Your book has been doing this since last chapter. You are now allowed to do this, but here's the rule. If you ignore x and you solve this equilibrium equation and you get an x value that is close enough to impact the original concentration, you have to go back and solve it the long way. Okay, and we're going to see what I mean here in 1 second. If we use this assumption, instead of plugging in 0.2 minus x, we're going to plug in 0.2, and we're going to ignore this x here as well. That simplifies what we're going to solve over here, right? Because then there's only one x that goes into our expression. So let's solve it that way and see what we get for x. Remember that this is my expression. We now have values for all three of these, right? So let's plug it in. That is a lot easier to solve than having something minus x on the bottom. Do you agree? Oh, yeah. All right. So let's solve this for x. I can get rid of my parentheses, right? We're going to talk about the rules for ignoring x here in a second once we get an x value. Yes.
Is a Ka a negative 4 or?
To the negative 4. Yes. Yes, ma'am.
You have a calculator for your chance?
I do. I don't have a block, though. Solve it the way you're supposed to. You should get the number on the screen.
Yes, sir. For ignoring the x on it,
That's what we're about to talk about. Yeah, that's what we're about to talk about. I want to see you get it first. All right, so now that you have hopefully gotten the same answer, the one on the board, in order to check and make sure that this number is small enough to have ignored x, Go back and plug it into the original equilibrium, 0.2 minus x. So take that 1.4 times 10 to the negative 3 and subtract it from 0.2. What you're going to see is you get a value of something like 0.199, okay? 0.199 is essentially 0.2. So what you're looking for is an x value that is at least 2 orders of magnitude different. It has to be 2 orders of magnitude different. If this was 10 to the negative 2, we could not ignore it. Okay? Because that would have a bigger impact on our original concentration than this one does. Does that make sense? Now, the reason we can ignore x for the most part in this whole chapter, and only in the situation where it's being subtracted or added to a number, is because our x values will come out to be small numbers. Does that make sense? So we're introducing a shortcut, right? This is the first of many shortcuts we're going to talk about in this chapter. Yes?
So can we use it even if we don't have like a number to substitute for the hydrogen ion?
Yeah. Now, I mean, you're talking about this situation, right?
Yeah.
Instead of this, though, you couldn't ignore x, right? You would have to do... Does that make sense? You can only ignore it when you have a number it's being subtracted from or added to. Does that make sense?
Yeah.
In that case, you'd keep the x. Yes?
When you say like 2 orders of magnitude, do you mean like 2 numbers?
So I mean 2 orders of magnitude. So this is times 10 to the negative 1, right?
Yeah.
This is times 10 to the negative 3.
Oh,
That's 2 orders of magnitude.
okay.
Okay? All right. Moving on. What was the actual question? What is the pH and what is the concentration of F? So this is the concentration of F, right? What is the concentration of pH, or what is the pH is the next question. So we're going to take that 0.1 and we're going to use the 0.1 molar. This even demonstrates to you, if we add the X value, it's still basically just 0.1, right? Because remember, it's a small number. So we're going to take the pH of that number and we're going to get a pH of 1. Yes, sir.
I'm confused on where the 1.4 times 10 to the negative 3.
You solved the expression up here for X.
So you multiply 0.2, right? Then
Mhm.
you divide by 0.1.
Mm-hmm.
I keep getting this, not that answer for my calculator.
Really? What do you keep getting?
0 or 1.0 or 0.00136.
Okay, so close though, right? Doesn't that round to 1.4? You're telling me you get 1.36 times 10 to the negative 3.
Not 1 point. I'm saying the number.
Right, you're telling me you get 1.36 times 10 to the negative 3,
0.00136.
which is negative 3.
It's
It's all good. It's the morning. All right, our next shortcut that we're going to introduce is a buffer situation. So buffers are going to be things that keep pHs within a certain range. If we are doing a type of chemistry that must happen within a certain pH range, we tend to create buffer solutions in order to monitor that situation or in order to create that situation. Okay? These are going to consist of a weak conjugate acid-base pair. They're very good at resisting pH changes over a very specific range. Once you get out of that range, buffers kind of lose their ability to do what they were designed to do. Okay? So if we have a solution, a weak conjugate acid-base pair, we're talking about a buffer, if you will, that is designed to keep a pH between 6 and 8, okay? And then we add acid. You're going to have to add a ton of acid in order to get that pH down. Okay, right? When we add acid, we're trying to lower a pH. We get that pH all the way down to 6, which is the limit of its range. After that, the buffer is no longer going to do its job. Okay, it's not going to resist changes in pH any longer. Okay, famous buffers. Your blood. Really good buffer. Okay, your blood is designed to keep the pH in your body at a certain level so that membranes, molecules, all of that stuff doesn't break down. Okay, when it comes to buffers, say we start with an initial solution. In that particular initial buffered solution, we have HF and its conjugate base, F minus. The whole idea of a buffer is that if you add acid or base, that all you're really doing is shifting your equilibrium a little. Okay? It's going to resist those changes. I expect more.
Oh, well, you will be disappointed.
Some days.
Lower your expectations. You get
That being said, the idea behind a buffer is that we're going to be able to use it in specific ranges, right? Now, if we pick the wrong buffer, we might not get the result we're looking for. But the beauty of our buffers is that they're going to introduce us to a concept called the Henderson-Hasselbalch equation. Who did their reading last night? Yeah, does it sound kind of familiar? A little bit. You heard his nice big German name. You like him because he helps you calculate pH changes without having to do this. Now, that doesn't mean you're free of this. You will be asked when something involves a buffer to use the Henderson-Hasselbalch equation. But again, it's another shortcut. Beauty of this chapter, all the shortcuts. Say again? Beauty of this chapter is we're introducing shortcuts, but you have to know when to use them, meaning you have to remember things you've learned in previous chapters in order to use them correctly. Yes, sir?
So I don't know if I'm just like being dumb, but like, and I understand that after calculating x, you got such a small number that it doesn't really matter.
Correct.
But in what situation would you actually use the shortcut of just not finding x? Because in that one, weren't you looking for the concentration of fluorine?
Yeah, so every situation moving forward.
So
most situations are going to result in an X change that is so small it doesn't impact the initial concentration.
So unless it's like asking for like the concentration of fluorine where like the answer is x,
Mm-hmm.
if it's asking for like pH, you don't even need to worry about it.
So remember, you can't necessarily assume X is smaller. We had to go through and do the calculation in order to figure out that X was smaller.
Yeah. So
Once you figured out X is smaller, yeah, you can ignore it for the pH situation only.
yeah.
But you cannot just make that assumption early on. I say you can assume X is smaller the first time moving forward.
Okay.
You cannot make that assumption and just say, okay, well, here's what the pH would be then.
So okay.
Does that make sense?
I think I understand.
When we say we can ignore X, we mean only until we can prove that it's okay to ignore X. We proved to ourselves it was okay to ignore this value by comparing it to the original number.
Yeah, you ignored it when you were calculating for pH.
Correct.
But I was just confused.
But you can also ignore it
Part of the
for this
answer
part too. Yeah. Yes.
So would you determine that by the final answer, 0.2 minus that, or would it be by the magnitude?
I would go with the final answer of this would be 0.2. Does that make
The
sense?
final answer has to be smaller than 0.2?
Hmm. Yes, like you mean the X value has to be 2 orders of magnitude smaller than what you would have subtracted it from. Yes.
So when we're doing this, we ignore x completely, and then if it has like a concentration, we just put that in for like the.
It has a concentration. No.
Not
Guys, we don't ignore X completely ever.
Well, like not.
We're saying we
completely.
ignore the change in X, aka the minus or the
Yeah,
plus.
Not
Okay.
completely, but like when we're like doing it, we just don't put in like.
You don't, right. So the first time you go through this, you can ignore the change in X. Once you figure out what X is by ignoring it, if it's small enough, okay, compared to the original numbers you were given that you ignored it for, then you're okay, right? You can assume that that happened and that that is the answer to whatever thing you were trying to find the concentration of at equilibrium. You cannot just assume that this is going to happen, though, is what I'm trying to tell you. You will not be able to ignore this in every situation. But in most situations, X will be so much smaller that it doesn't impact your original numbers.
And so the thing, like the shortcut is that you therefore don't have to add x.
Right, so the shortcut is that you don't have to solve the really long quadratic.
Yeah.
Right, because originally what would this have been?
Something terrible.
we simplified that expression by ignoring the subtraction of x and the addition of x down here.
Yeah.
Okay? Then we solved for x, and we got a pretty small number, compared it to the original number, and decided that this would be this,
Yeah.
which is approximately 0.2. So what we did here is we justified that we could ignore x.
Yeah.
Does that make sense?
But you still already did the work, right?
Well,
In finding-
I didn't do like this work, but yes, I did do something with Ka in order to find what x was. Yes. Go ahead.
So if the number in the green was bigger than that 0.2, then you would have to go the long way.
Correct.
Okay.
Correct. If this was a bigger change, then you can assume. Does that make sense? So if we got like 1.4 times 10 to the negative 2, this becomes 0.018. That number cannot be rounded up to 0.2 the same way. That number is a significant change from the original value. Does that make sense? If this happens, you have to go back and do this.
So it pretty much has to be exact. It can't be less or more.
Should be very, right.
I
Right.
know, that's what I'm
Yes.
saying.
If we do the
That's
long
literally
way,
what-
are we gonna get the same answer?
You're going to get a different answer. If you do it the long way, you're going to get a different answer for x.
So then how
I
do we
understand.
ignore it?
so.
I get what.
So you can so what we're saying is this doesn't impact that enough to matter, right?
So like if we're looking for the concentration of F,
Correct. But if you get, so like let's say you get something that's really close to the original value, right? Like let's say you get 0.014,
yeah.
which is what we were just saying. Then you get this value instead for this change, which means you have to go back and ignore this, do the whole long thing. Because your x value does matter in that case for the change in this. It would also matter for this particular number, which was one of the things you had to use, right?
Yeah.
So it would change your pH significantly. Yeah.
That's dumb.
You hope you don't find that situation, I guess, is the moral of the story. Back to buffers. All right. So buffer calculations, again, another time where we can use a shortcut. In order to understand how to use that shortcut, I'm going to remind you of the generic form of an acid equation. So you're going to see that the acid is added to water. Remember, you ignore water in your expression. Makes your conjugate acid and your conjugate base that lacks the proton after it has donated it. Please remember that in this particular chapter, we are assuming acid base is Bronsted-Lowry. Okay? For the most part, acid base is Bronsted-Lowry definition. The one exception to that is NH3. Okay? NH3 is a Lewis base that also is a Bronsted-Lowry base that has that lone pair. So just remember, we're focusing on Bronsted-Lowry, which really just means proton donor, proton acceptor, right? Don't forget that. All right, so here is the form of Ka for any acid that follows the Bronsted-Lowry definition. Do you agree? Look familiar? Okay. When it comes to buffer calculations, remember that one of our rules is that we're trying to find a range of pHs. And the Henderson-Hasselbalch equation is what we're currently trying to get to. So here we have a rearranged form of the Ka equation that has H3O plus kind of moved away from the acid and the base. Does this thing up at the top look just like that at the bottom? Do you see the difference? All we did was take this term and move it away from the rest of the fraction. A slight algebraic manipulation. From there, we then took the negative log of everything. Reason being, when we're talking about buffers, one of the major concepts is that they are pH manipulators. So taking the negative log of the H3O plus concentration makes it a pH. Doing this operation produces the Henderson-Hasselbalch equation. That's the one at the top. The one right below it is a rearranged version. Do you see that? This gets rearranged to this. What is a pKa from last chapter? I hear this is a thing that challenged us on our quiz. It's the negative log of the Ka. That's all it is.
I don't know what that.
Anytime you see that P out front, all it means is take the negative log. Please remember, those little brackets mean concentrations. In this particular Henderson-Hasselbalch equation, we can calculate the pH of a buffer, only of a buffer. We calculate the pH of a buffer by taking the negative log of the Ka, adding it to the log of the concentration of the base over the concentration of the acid. All right, so let's do practice. Here's our question. It says, what is the pH of a buffer? That is how Henderson-Hasselbalch equations start. In being asked any question about a buffer, the first thing you should locate is the Henderson-Hasselbalch equation if you don't already know it. Since it says what is the pH, I am going to use the version of the Henderson-Hasselbalch that puts pH out front. We are told that lactic acid has a concentration of 0.12 molar. We are told that the lactate ion, also known as sodium lactate, remember that the lactate ion would be the conjugate base, is 0.10 molar. And we're told the Ka is 1.4 times 10 to the negative 4. So do we have everything we need to use the Henderson-Hasselbalch buffer equation? Do we have an acid? Do we have a base? Do we have a Ka or a pKa? We do. So do the math. Anytime you see the term P, you put a negative log.
What does the P stand for?
I don't really know. It's like an operation.
Alright.
I think it's just like a placeholder for an operation.
Right.
It's kind of like, what does E stand for? Like an
I'm not
irrational
sure.
number, you know what I mean?
Yeah.
Or an ln. It's like
Stands
natural.
for E.
Stands for like an operation you're supposed to do.
It's a E.
All right, log of base.
Noise.
Again, this is a shortcut for you to be able to skip equilibrium chemistry. Could we go back through and solve it as if it were an equilibrium chemistry problem? Using Ka's, the expression, the equation? Absolutely. That it would take us a lot longer, yes?
If we had like a pKa instead of a Ka, we would have to do the negative log.
You would have to do negative log, right? Mm-hmm. Good question. But a lot of times you're going to get acid-base information in terms of Ka's. Okay? All right. So that was the first two things in this section. All right, let's talk about pH ranges. There are going to be a set of pH ranges where each buffer is effective. We can pick a buffered system by comparing pKa to whatever pH we want our equation to take place in. We're going to prove to ourselves that when we add strong acids or bases to a buffer, that the buffer does exactly what it's designed to do and resists those large changes in pH. And we're going to do this by looking at things in two ways. The first is going to be a Henderson-Hasselbalch equation to introduce what the buffer is and what the pH of the buffer is. The second is to actually see what happens when we add a strong base to that buffer. Two-step process to do this. Kind of two steps. First one says to determine the neutralization reaction. That's the very first step. That can be kind of the most challenging part of a lot of these different problems. It's to figure out the actual reaction that's taking place. The second is going to be to use the Henderson-Hasselbalch to determine what the pH of the solution should be. In other words, what we're saying is we have to start with a balanced equation and an ice table to figure out what happens at equilibrium before we can plug stuff in to the Henderson-Hasselbalch. Fancy way of saying that. We're going to start with an ice table. We're going to move into Henderson-Hasselbalch. And we're going to use the principles of strong acids and bases to help us understand what happens as far as the change is concerned. So what does it mean to be a strong acid or a strong base? What's happening?
It's dissociating fully in water.
It is 100% dissociating, meaning 100% reacting. There will be none left over once that thing does what it was meant to do. Here is our question. It's a long one. It says, a buffer is made by adding 0.3 moles of an acid and 0.3 moles of the conjugate base. You know this is the conjugate base because this ion is the same one present in the original acid. Okay? In order to make a 1 liter solution. Why were we given moles and then liters? What do we typically deal with? Molarities. If we have moles and liters, we usually have to put them in molarities. Mole over 1 is going to be the same number, right? So in this case, does the volume of the solution really matter? It does not, because it's 1. If it was not 1, would it matter? Yes, it would. The pH of the buffer is given to be 4.74. We are asked to calculate the pH of the buffer, or the solution, after we add some of this strong base, 0.020 moles of this strong base. So first things first, we were already given the pH of the solution for this particular buffer, right? We know that that pH is correct because the moles of the base equal the moles of the acid. 0.3 moles of one equals 0.3 moles of the other. We were told that, right? At the beginning of the problem, we were given 0.3 and 0.3. If I try to take the log of 0.3 over 0.3, what is the log of 1? 0. So this whole term goes away, and pH equals pKa. So that's why this says pH equals pKa for this particular solution. Only when the acid and base concentration are equal will it become the log of 1, which is 0. Could you do that yourself? Absolutely. But we were told this information already. We were told the pH of the solution is 4.74. All we're doing is proving it. So now we do the complicated part. We get a reaction. We know that we're adding the acid to that sodium hydroxide, which is a base. We're going to form the conjugate ion and some water. There's our reaction. Why did we know this one? Because we were told we were adding to a base. If we were adding to an acid, would things be different? Yes, it would. All right, then we set up an ice table. But in this case, we really don't have to do much for the change because we know what the change is going to be based on the fact that a base completely reacts. All of this is going to get used up. So if we were to do an ice table, what would it look like? Let me erase this. Set it up in your notes. We know what this is. We know what this is. We know what this is. And we don't care about that. All right. You agree? We were told this is a strong base, right? So at equilibrium, this has to go to 0. If we know 0.02 minus x equals 0, what is x? When we deal with strong acids and bases, they completely dissociate, meaning completely react. So now we know what x is, right? We were asked the pH of the solution after the addition of the strong base. Do you agree that after the addition of the strong base, we're at equilibrium again? Mm-hmm. So we're going to use these values in our Henderson-Hasselbalch to determine what the pH change is. Now remember, we have the pKa from before. It was equal to the pH. So our pKa was given to be 4.74. So the next thing we're going to do is we're going to plug what we know in. Our base concentration is the bigger of the two. It's the one on the left or the right. After the addition of a super strong base, the pH went up by 0.06 units. AKA the buffer did its job. It wasn't supposed to allow huge changes in pH. That is what a buffer is designed to do. You can add strong acid, you can add strong base, the change should be small comparatively. No, it's not. All right, we're going to take a break and do some practice. We're going to cover section 3 tomorrow. I mean, we're going to take a break from new topics and do some practice problems. I have a whole nother section to cover. Haven't even got to it. Yeah. Take your 5 minutes. 48. That means before the bell, boys and girls.